Trigonometric equation, this part of it's fine. Quadratic in tan, that's no real problem. It's this little part here that creates the difficulty. Now these three additional trigonometric functions that we've introduced come from a day that predates calculators. Back in my school days, which was a long time ago, all these calculations would have been done using four-figure tables. Now, all the trigonometric values that you use for sine, cosine, and tangent would actually come out as 4 decimal place tables. And so the accuracy, and if you imagine you had to divide by a 4-digit decimal, that's actually quite difficult. So what we had was the reciprocals of those trigonometric functions, and you simply multiply by a reciprocal. So it's a sleight of hand if you like, but it's worth remembering that cot of an angle is 1 over tan of the angle. Now you notice that I said the reciprocal, and the notation here would be tan minus 1, but because of calculators we don't use tan minus 1 per se, because when you look at a calculator, tan minus 1 means give me the angle whose tangent is 1, or give me the angle whose tangent is, as opposed to the reciprocal of tan. And really what this should be on the calculator is arc tan, r sine, and r cos AR, but that doesn't fit on calculator keys. So cosec, cosecant is 1 over the sine of the angle, and secant is 1 over the cos of the angle. So these are reciprocal functions, and the idea is that you can multiply by a 4 decimal place figure much easier than you can divide by it. So it's also worth remembering the standard Pythagorean setup, where if I have some angle, then obviously the opposite side there is the sine of alpha. This adjacent side here is the cos of the angle, cos of alpha, because I've set up a hypotenuse of 1, and that gives us our classic cos squared alpha plus sine squared alpha is equal to 1. If I divide that through by, first of all, cos squared, and I'm going to write c squared rather than cos squared, I'll get cos squared over cos squared plus sine squared over cos squared is equal to 1 over cos squared, and clearly that gives me 1 plus. Now we also know that tan is sine over cos. Reason for that being fairly simple and straightforward. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse. The over hypotenuse bits in bits cancel, giving me opposite over adjacent. Therefore I've got tan. So therefore I've got sine squared over cos squared, which is tan squared. And now I've got 1 over cos squared, which is sec squared. You notice I've stopped writing s's and c's now because I've got sec, and it'll confuse my little brain. If I divided through by sine squared, going back to my original cos squared plus sine squared equals 1, I'd get cos squared. Oops, I won't put the whole of that. Cos squared over sine squared plus sine squared over sine squared is equal to 1 over sine squared. Cos squared over sine squared is cot squared plus 1 is equal to cosec squared. Doesn't matter what angles I was using there because these are true for all angles. But clearly what I need in this particular case is that one there, because now I can make my equation work much better than it did before. So instead of having 2 tan squared theta plus 2 tan theta minus sec squared, I can replace that by 1 plus tan squared, because I have actually just developed that particular thing, and that's going to be equal to 2. So all I've done there is I've used the fact that 1 plus tan squared is equal to sec squared. I've bracketed it because of the negative sign that distributes. I just have to be a little bit careful. But expanding it out, I'm going to get, I do wish it wouldn't do that, 2 tan squared theta plus 2 tan theta minus 1 minus tan squared theta minus 2 equals 0. And I always like to get my equals 0 in there, because when I'm dealing with quadratics, because I'm reliant on the fact that a times b equals 0, the implication is there that either a equals 0 or b equals 0. You need that equality to 0 in every time. Get it in early if you can. Don't forget to put the equals 0 in, because it will cost you otherwise. 2 tan squared, take away tan squared, gives me tan squared theta plus 2 tan theta minus 3 is equal to 0. And rather than cram it all in, I am going to go on to another page. So my quadratic is 2 tan squared theta. No, it's not. It is only tan squared theta plus 2 tan theta minus 3 is equal to 0. Most of these trigonometric quadratics will factorize. Remember, typically with a quadratic you're expecting 2 solutions, but because it's quadratic and trigonometric, you would expect twice as many solutions. So therefore you ought to always have principal values and secondary values, so therefore anticipate up to 4 solutions. Not in every case, but anticipate that. They factorize quite nicely. Obviously, in order to get the tan squared theta at the front, I've got tan theta and tan theta. To get that minus sign, I need a plus and a minus. And the fact that 3 is obviously a prime number, the only ones I've got are the 3 and the 1. That's the only pair I can actually have. So I put the 3 in there, I put the 1 in there. So my implication now is that tan theta plus 3 equals 0, which gives me that tan theta equals minus 3, which is fine with tan, because it's opposite over adjacent. I don't have to be restricted to less than zeros, or less than 1, sorry. Tan theta minus 1 is equal to 0, which gives me that tan theta is equal to 1. Now you really should know the angle whose tangent is 1. So you notice I'm writing arctan because that's what I said earlier. If you write tan to the minus 1, that's fine. So therefore theta is 45 degrees. You think about your classic 1, 1, root 2 triangle. Classic 45 degrees, or pi by 4 radians, whichever you prefer. But that's the principal value. I also need a secondary value for that. Now, depends whether you actually think about the graph of tan. So here's my one rubbish diagram, but the next one, because of the periodicity here, is 180 degrees further on, so it will be my principal value 45 plus 180, so therefore two of my answers, 45 and 225 degrees. Notice I didn't use a calculator for that, which is not unusual. Other way of doing it is using the trusty cast diagram. I've got one solution in here at 45 degrees, and because it's tan, the symmetry is diagonal, so the other one will be 180 degrees further on. No real problem. Now, this is the only one I need to use a calculator for. Okay, so here my theta is arctan -3. The minus is important, and this is the one where I'd use a calculator for it, so I'll get -71.56505115018. Okay, that's my principal value, but it's not in the range that I require, because the range I require is that theta is between 0 and 360. So clearly what I've got here is, there's my -71. So it's going to be 360 minus 71, which gives me, technically my principal value is 288.4 degrees. Now notice that's a rounding, and my secondary one, because I said the symmetry was diagonal, is going to be 180 degrees off that, so 108.4 degrees. To one place is a decimal, in decimal. Okay, no real problem, but 4 solutions, not unusual to have 2 that you should know, and a couple. I'm quite happy under exam conditions that this notation I used, arctan of -3, is exactly the same as your calculator notation, -3. And give me the angle whose tangent is -3 is what you're telling the calculator. You're not telling it the reciprocal.
So I'm hoping this will be interesting for you. We've got an arc of a circle of radius 1, as we can see from the line A to C, which is length 1, and that's a radius. And we can start putting the trigonometric functions onto this diagram. So first of all, the basic ones, which you'll have seen before. We've got that CB over AC is, in relation to theta, the opposite over the hypotenuse, so that is sine theta. And since AC is 1, that tells us that CB is equal to sine of theta. So I'm just going to write sine on there because we don't need the theta. These are all related to theta. Now, for the cosine, we have AB over AC, so that's cosine theta. And again, AC being 1 tells us that AB is cos theta. So that means AB is cosine, but actually you'll see parallel to AB we have the red line emanating from C, so that's what I'm going to label as the cosine. So we have the cosine here. Okay, now we're going to consider the triangle ACE. Now that has a right angle at C, so the angle ACE is 90 degrees, and that means that CE is the opposite in this triangle and AC is the adjacent. So we have opposite CE over adjacent AC, which is going to be tan theta. And that means, because AC is equal to 1, we have that CE is equal to the tan of theta. So that yellow part is the tangent. So sticking with ACE, we can note that cos theta is the adjacent over the hypotenuse, and since sec theta is 1 over cos theta, this is the hypotenuse over the adjacent. So in the triangle ACE, the hypotenuse is AE and the adjacent is AC, so that must be sec theta. That tells us that sec theta, again because AC is equal to 1, sec theta must be equal to AE. So we can label the green line as secant, which is the full word for the sec. Now we can chase angles round because we've got right angles, and that's a bit like something we have to do in mechanics sometimes when we're working out components of forces. But in this situation, what it means is the angle at A in the triangle DCA, so we'll be having a look at the triangle DCA, then that means the angle at A will be 90 minus theta, so we can put that in there. We have a right angle at C, and therefore the angle ADC must be theta, so we can put that in up there. And now we see we've got another right angle triangle, this DCA triangle, with an angle theta in it. So we can do some more trigonometry. So if we think about sine theta, so sine theta is opposite over hypotenuse, and cosec theta is 1 over sine theta, and that will therefore be the hypotenuse over the opposite. Now in the triangle DCA, the opposite is 1, so this time we've got AC at the bottom there. So anyway, we can say that cosec theta is equal to the hypotenuse, which in this triangle is AD, over the opposite, which is AC, is cosec theta, and this tells us that cosec theta, again using the fact that AC is 1, must be equal to AD. So the pink line is called the cosecant. And then finally we have the fact that since tan theta is the opposite over the adjacent and cot theta is 1 over tan theta, that must be the adjacent over the opposite. And in the triangle DCA we have the adjacent is DC, So we have DC over AC, which is the opposite, and that's equal to cot theta, which tells us that cot theta equals DC, since yet again AC is 1. And that means this purple section is the cotangent. So that's where these things lie on the unit circle. We already knew where cos and sine were. You may have seen the tangent being shown as the section from C to E. Note, of course, I'm not sure if I mentioned, but the line DCE is a tangent at the point C to the circle. And so we have the tangent coming from C down to the x-axis there. But you may not have seen the secant, the cosecant and the cotangent on the unit circle. And now you have.
So, having established where we can see the lengths for the sine and the cosec, the cos and the sec, the tan and the cot, then on Geogebra we can have a little play about with this. So the interesting thing, and this is some really nice geometry, is that we know that, for example, or starting with, the sine times cosec must be 1, because cosec is 1 over sine, sine times 1 over sine is 1. And so that means that if we draw a tangent to a circle, so the DCE line, then the sine dropping down from the point where the tangent is, times the distance from 0 up to where the tangent hits the y-axis, when we multiply them together we must get 1. So let's try taking this down, or up rather, so we get a sine of 0.8, and you may know, but you can check with the calculator, 0.8 times 1.25 is 1 1/4 times 0.8 is going to give us an extra 0.2 for the quarter, which gives us 1 altogether. So if we slide this round until the sine is 0.8, then we have the cosec being 1.25. For the cosine, we could take that down to let's say 0.4. Oops. And then we have 0.4 and the sec being 2.5, and 2.5 times 0.4 is indeed 1 as well. And then for the tangent we could make the cot into 0.4 as well, and because these numbers are rounded off I have to jig about a bit, but we've got cot being 0.4 and tangent being 2.5. So it seems to me, whoops, that there's something very beautiful about the fact that because the radius is 1, these various things multiply to give us 1. And we can see how trigonometry and, if you like, pure geometry meet there, because we can construct these various lines without using angles. The line for sine is simply the parallel line dropped down from C, parallel to the y-axis, and then we can draw a tangent on, again without trigonometry, and we find that the distance from C to B times the distance from D to A is 1. And similarly for the other properties that we've found. So if you're into geometry, I hope you've enjoyed this, and if you're not into geometry or weren't into geometry, then maybe you are now.